Good evening. This is the solution video for that homework question. So I tell you that this apparatus is designed to determine the coefficients of friction, um, and it's shown to the right. The box is slowly rotated counterclockwise, so it's slowly rotated in this direction. When the box makes an angle theta, that angle theta, with the horizontal of the block of mass m just starts to slide, and at that instant the box is stopped from rotating. Thus, at angle theta, the box slides distance d, at distance d. Hits the spring of force constant K and compresses the spring distance x before coming to rest. So they're asking us to draw a qualitative energy bar charts that represent the energy of the block earth spring box system at the locations indicated. So block, earth, spring, and box system. Okay. So that means that energy transfers are happening to different components in this whole system, right? So let me start with the system. Let me start by looking at this block in the initial stage, looking at this block as the system, right? If I'm looking at this block, because in its initial stage, it was resting perfectly at this pivot, right? It was resting at this pivot like that. So in its initial stage, you can say that if you're considering this position here to be your zero, if you're considering this as your zero, then it doesn't have any gravitational potential energy. And technically, it also doesn't have a gravitational potential energy, even if you're considering this to be a zero, because it's still supported by this thing, right? And since it's just flat, you could say the only way it would have energy is if this thing was going to get out of the way, but it's not. So even if this was my zero, you could say it doesn't have gravitational potential energy. But let me use this as my zero and say that at this position, it has no gravitational potential energy. So since it's moving counterclockwise, there is motion counterclockwise, I have what we call rotational kinetic energy, but we'll talk about that later. The issue, the point is, or the fact is that since it's still moving, it does have kinetic energy since it's moving counterclockwise, right? It does have kinetic energy. So in the initial state, all of this energy is due to kinetic energy, right? Because just like we've explored, I don't have any gravitational potential energy because I don't have a change in height at this position. Now, when x is equal to d, what did it say? That at this angle theta, the box slides the distance d. When x is equal to d, this box is going to slide the distance d, and the box will be somewhere here, right? So when x is equal to d, is the box, and since there is friction involved, I know friction removes work from the system or from the whole system by turning that work into heat. So I expect to have some thermal energy at this position. X is equal to D. I expect to have some thermal energy, right? Now keep in mind that the total initial energy was was kinetic energy. And since I've used 4 blocks to represent the total initial energy, my total energy here should also be 4 blocks. So I know that since it has moved the distance d, friction has done work on the system, so there's going to be heat. We can represent it with that. I also know that, what else do I know? That at d, when it is at position d, right here, it has moved the distance d, it's still moving. So it still has some kinetic energy, right? It still has some kinetic energy. Now, depending on how I drew my thing, right, I could make these 2 blocks, and I'm going to reduce this to be 1 block. I'm going to reduce this to be 1 block for thermal energy. The idea is that you have all of your blocks equal to the initial energy. And the only thing missing is potential energy, right? Now, when this system starts moving counterclockwise, this block gains potential energy because its height above its initial position, this height is increasing, right? Now, granted, as this block slides downwards, its potential energy is decreasing, but even still at this position, because at this position you could have counted its potential energy from this point, from the center of gravity, and now at this position it still has a potential energy from its center of gravity if you're counting this as your zero position, and even if you're counting this as your zero position. So it still has potential energy due to this height right here. So it has a little bit of potential energy. So that's going to look like that. And all my bars are adding up to be 4. So I'm good. Then when the extension of the spring is equal to the compression, when x at this position, when x is equal to the compression of the spring, because it said it hits the spring compressed at distance x, right? So at this position, when it's compressed at a distance x, I know there's going to be elastic potential energy, right? Since still friction has been doing work even up to that position, I'm going to have some kind of thermal energy because that's accounting for friction. So that, what am I drawing it down here? Why am I drawing it down here? Okay, so I have thermal, I have elastic, so those are 3 blocks. And what else do I have? Do you guys think I have any other form of energy at this position when the mass has compressed it at distance x? Let's say now the mass is over here. Do I have a height above my initial position? No, I don't have a height above my initial position. So I'm not going to have any potential energy. Since it's at rest, I won't have any kinetic energy. So the only 2 energies I have are thermal energy and elastic potential energy. Now, I don't think these 2 energies will be equal, so I'm going to draw my elastic potential energy being greater than the thermal energy. I know this might be confusing, so a good way to start is to try and do this same problem without friction, right? Do the same problem without friction, figure out what kind of energy transfers are happening, and once you're able to do that without friction, once you add the friction, it might be a little bit easier. In a subsequent experiment, second block with a mass 2m is subjected to the same conditions as the original block. The new block is made of the same materials as the first block. Indicate how the values of the quantities below will change in the second experiment. So how does V change in this second experiment? The speed of the block just before it, or even before it goes into the spring. How does that change? So we know that on an incline, right, when an object is moving down an incline, its acceleration, it has a force mg sine theta acting that way, component of force, and since it has friction, you have friction force going that way. Its equation of motion will be mg sine theta minus friction, which is mu mg cosine theta is equal to ma, because this is coming from F net equals ma, and the F net is the downward force minus the upward friction force. So I hope you can see that m is common to each of these items, and its acceleration will be g sine theta minus mu g cosine theta. So the acceleration is independent of the mass. Since the acceleration is independent of the mass, that tells you that the speed is also independent of the mass, because v is equal to u plus at. The u is 0, so the v is going to be equal to a times t. The v is independent of the mass because acceleration is also independent of the mass. So, and you still know that they take the same time to fall downwards because they are still, the time is also still independent of the mass. But this one is just trying to talk about speed. And let me use an equation that doesn't have time so that you can see it. If I use v1 squared equals v0 squared plus 2as, right? They are falling, or 2ad in this case. The v0 is 0, so I have v1 squared is equal to 2ad, right? Both objects, this equation has nothing to do with mass, but it has something to do with acceleration. However, we have shown here that the acceleration is also independent of the mass. Now, you don't have to use all these equations. I'm just using this to explain this to you. But all you have to say is that the v will remain the same, right? Why does the V remain the same? Is because you can say V is independent of mass, right? And you can explain it because where this question is trying to pull you is into thinking that bigger mass leads to bigger friction. Bigger friction, that is true. Bigger mass leads to bigger friction on handwriting. I know Michael is complaining right now. So bigger mass means you'll have more friction, right? However, bigger mass also means you'll have more, more gravitational potential energy, right? More gravitational potential energy that is gained when the thing is lifted and converted into kinetic energy and thermal energy. So the two gains cancel each other out, and then you end up having the same speed at the end. You have the same energy conversion from potential to kinetic for each particular mass, and therefore you have the same speed at the bottom. So the speed is going to remain the same. And finally, what about the compression of the spring? Well, a bigger mass, right? A bigger mass compared to a smaller mass, even though they both have the same velocity, what do you think is going to happen to the compression of the spring with the same spring constant? What do you guys think? Just intuitively, I think, and even if this is not on an incline, even if it's just a mass falling from above, falling onto a spring, right? A big mass and a small mass. Since they're both acted upon by acceleration due to gravity, they have the same acceleration. So by the time they get to this position, they will have the same speed, right? They'll have the same speed. But just physically looking at this, which of these two masses do you expect to cause a greater extension in the spring? It's the bigger mass. Why is it the bigger mass? Because this bigger mass has a bigger gravitational potential energy, and all of that gravitational potential energy is going to be converted into elastic potential energy, right? So this one has more gravitational potential energy, means it converts it into more elastic potential energy, which means you get more extension on the spring, versus this one, which has lower gravitational potential energy, which converts into lower elastic potential energy, which converts into a smaller extension on the spring. So you expect the extension to be smaller, to be decreasing. No, wait, increase, yes, more extension. I hope I didn't confuse you there. Bigger mass causes more extension, smaller mass, less extension. So yeah, that was that one.